When our web servers are busy, or when we have multiple requests from the same local network to the same origin servers, we sometimes find it useful to use a proxy server. This could happen in a university campus, a company, or a residential ISP where users might, for different reasons, refer to the same web server very often. The goal of a proxy server is to satisfy client requests without involving origin server itself. This option, when cache installed by ISP and the option chosen by the user at the browser, allows the HTTP request to receive the object from the cache instead of requesting it all the way from the origin servers. This means if the object is available at the cache, the proxy server responds to the request locally, and the request will not be sent to the origin server. If the object is not in the cache or it is timed out, the request will still go to the origin server, and a copy of the response is stored in the cache with the new response. Web proxies act as both client and server. Server for original requesting client, and client to origin server. But why would an ISP implement such a mechanism? Web caching is an inexpensive way of reducing access link usage and the response time to client requests. That makes web caching a cost-effective choice for bringing content to the user. Let's examine the effectiveness of web caching through an example. Assume we have an institutional network with line capacity of 1 gigabit per second locally. The edge router of this network is connected to the public internet with one access link with capacity of 1.54 megabit per second. The average request rate from browsers of the users in this network to origin web servers is 15 requests per second, with average object size of 100 kilobits. Round-trip time from institutional router to any origin server is 2 seconds. Based on these assumptions, we can see that the average data rate to browsers is 1.5 megabit per second, which is found by multiplication of requests per second and average object size. The utilization of the 1 gigabit per second LAN serving 1.5 megabit per second will be pretty low, which is good. However, access link utilization that has to serve the data rate of 1.5 megabit per second with 1.54 megabit per second capacity will be close to full capacity. And remember from performance discussions that this means long delays on the access link. One solution to this problem could be increasing the access link capacity. For example, we can choose a link with 100 times the previous capacity, and that would easily bring down the delay from order of minutes to the order of milliseconds. However, this would be a very costly upgrade. The second solution, which is a lot more cost-effective, is deploying a web cache. Suppose the cache hit rate is 0.4, which means that 40% of requests could be satisfied at the cache, and 60% of them still have to be sent to the origin servers. This reduces the access link utilization to 0.58, which drops the traffic intensity and therefore the delay to the order of milliseconds. The solution works well, and it is inexpensive. In order for caching mechanism to be effective and efficient, it needs to respond to the user with an up-to-date version of the object requested. This could be done using conditional get. In this way, the client can double-check the cached copy with the origin server and get an update if the requested object is modified since the date indicated.